Okay, hello. So I'm going to start my presentation for today. I'm going to put this in presenter view. So my name is Rosa Romero, and my affiliations are the University of Porto and also a spin-off company which is called Sphere Ultrafast Photonics. And today I'm going to talk to you about ultrafast lasers in different applications, namely in imaging and therapy. As most of you know, because my colleague Dr. Elder Crespo in the previous talk about, Porto is located in the southwest of Europe, in a very nice city. And this is the downtown of the city, how it looks like, and I really strongly to visit whenever it's possible, because at the moment it's a little bit complicated. Also because the city has the river, it also has the sea, and you can have a wonderful time in here. But our talk for today is related with ultra-short light pulses. And this happened to be the fastest events on Earth. So basically, an ultra-short pulse is a pulse which is very, 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 very short as 10 times to minus 15 seconds, which is 1 femtosecond. And you can see that this is how the electric field would look like for this super short pulse. And as it has been previously stated, a very short pulse has a really, really, really broad spectrum. So we have a lot of frequencies included on these laser systems. And these frequencies have the characteristics that they all arrive at the same time. And this is what makes these pulses so special and so useful for many different applications. So as I say, the very important properties of these laser systems are the duration and the intensity. And this means that we are able to get temporal resolutions because we have very, 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 very short pulses. And because they are super intense, we can excite in a different way from other laser systems. And this includes to ionization, the manipulation of matter, attoscience, including spectroscopy, many, many, many different applications. And these applications can range from cutting-edge research, so there is a lot of laboratories over the world that use these ultra-short femtosecond lasers for their experiences, or they are nowadays being used more and more often in health and life science, where they can find very interesting applications, as I'm going to show later on the presentation. They also have quite an important presence on material processing because of their characteristics of being really very, very, very short and with a high peak power. Okay, and this is why we are going to understand why we want to use femtosecond lasers on several applications. So here you have a time scale, and here you have the barrier of the picoseconds, microseconds, and here 10 times to minus 15 you have the femtosecond scale. And what really happens here on this barrier is that when you go shorter in time duration, the thermal effects are practically suppressed. Therefore, with a laser system, you can cut or drill without burning what you are trying to cut or drill, either a matter, either tissue, or different type of substrates. It happens that they have a high intensity, and this means that the materials have a non-linear absorption with these laser systems. So here we have two different images, and this is the example of a microscope. And when you have a long pulse, because it's very long and the peak power needed is quite high to be able to do a nonlinear process, it happens that because of the amount of average power that you are putting on the material, you are damaging the material, you are doing shock waves, microcracks, and then you have a heat zone that is destroying the material. However, if you use very, very, very short pulses, the affected zone is reduced to a smaller portion of the area. So this means that allow us to working in 3D inside the material, because we can pass the laser system without even altering or changing this surface, while we can observe here on this part of the material below the surface, or we can do changes on the characteristics of the materials. And to be able to do that, we need less energy for the same peak power, because what it matters in these applications I'm going to talk about is the peak power, the effect of, or the cost, what they cost, the nonlinear effects. And this is very, very, very important. Okay, still putting some information on why we want femtosecond lasers is because when you have a really short pulse, you have an enormous amount of frequencies that composes this pulse. In comparison with a very long pulse, you have a very narrow spectrum, so lower number of colors that you have when you have a longer pulse. And this is also very important because whenever you have more colors, you can also excite different, for example, in microscopy, fluorophores, because they have different absorption bands. So this is very important. However, there is a problem, and Dr. Albert Crespo already talked in the previous talk that whenever you have a very, very, very short pulse, these pulses are really, really, really very fragile. So you need to be very, very, very careful with the dispersion of these pulses when they propagate through media. And this is something that it has been working over time, and there are nowadays very interesting techniques and very, very precise techniques to measure and control these pulses. So we are able to use these femtoseconds laser pulses nowadays in the different applications I'm going to show. And this is very important because this is a period of 10-15 years that we could not use these femtosecond laser systems in applications because we were unable to control them. We were unable to make it perfect at the sample of the application. We were able to extract all the nice characteristics of being very short in time with a high peak power. And this is what really matters about femtosecond lasers, that we can use these properties. And these properties of a very short pulse and very high peak power allow us to going through into new physics. It's different physics, and we have to deal with the phenomena differently because we don't have heat, we don't damage the surface. So this is why it's different, and this is why they are so interesting for several applications. So just to show you an example, so basically this is our amplifier system at the Femto Lab at the University of Porto. This is the heart of the laser. This is where is the crystal for generating the amplified systems. And I'm going to show you a video of how these systems interact with matter, just for give you an example. So this is again this is the laboratory. So here is the amplifier system, and the beam is coming to this mirror here, and we are going to unblock. And now with this laser, we are ionizing the air. So this is how it looks, the far field of this ionization. And we're going to use this to do some things. So here, as you could see, there is the laser focused on air, and because it is so intense that we are ionizing the air. And what is going to happen is that we are going to cut paper with this laser system. And as you can see, it's not burning. I mean, we have a little bit of the smoke, but it's not burning. And a close view of the image is that you can see here that the paper is cut, but there is no ablation, there is no burning. And this is super important because whenever we want to use this in a tissue, we want to be very precise, and we won't burn all the tissue around. We want to have the tissue as healthy as possible, and we want to be very precise on the cut and on the areas that we want to work around. So, for example, Dr. Adela Benjakar, she's a collaborator of our group. She's doing in her group endoscope that it can be introduced in some parts, or can be introduced inside, for example, the body. This is it's not a real size, so this is very small. So you can introduce inside the body, and you can do tissue ablation on the inside the body, where other scalps, like the manual scalps, can do it with a normal doctor does. So the thing here, the important thing here is that you can have a probe that uses a femtosecond laser to be able to access very difficult areas of our body where there is some pathology, a cancer tissue or a damaged tissue that needs to be removed. And with these laser systems, we are able to remove the damaged area without burning around. So it's very precise. Another important thing that we can do with these laser systems is that there is now a trend in many different research labs that they are going to really ultra high intensity lasers that are able to provide intensities comparable to the intensities needed on an accelerator, like for example CERN, that has several kilometers of diameter, and they need to put the particles around this circle to be able to accelerate it. The idea here is that the use of ultra-fast lasers, so they can be focused and they can accelerate particles in a very short distance and with high intensity energies. And there is a trend nowadays of using these ultra high intensity lasers also for doing proton therapy, and to replace these very big facilities which are called synchrotrons, and you only have maybe 60 or 70 around the world. And the idea with these very high intense laser systems and very short pulse durations is that you can fit these lasers in a room, and you could provide every hospital with this technology so they could treat these areas using proton therapy. Because, for example, proton therapy also has the particularity of being very direct and very precise on the area they need to treat. Because, for example, X-rays, they have to illuminate a wider area, and this is also bad for the tissues and for the patient that is using this therapy. And this is very promising. Another important application of femtosecond lenses is optical coherence tomography. This means that you have an ultra-fast laser system also with the measurement and control, because you have also here optics and dispersion that need to be accounted. So you really need to have a control system to be able to provide these characteristics of the ultra-fast laser system as nice as possible to the target of the eye. And here you can do imaging on the back of the eye without taking out the eye and without damaging the eye, because the eye, the volume of the eye is transparent to this wavelength, so it's not interacting with the laser system and it's not providing any damage to the eye. So it's very interesting because you can do real-time imaging while you are doing the scanning, like with the eye blinking. So it's very also very spread among the ophthalmologists and doctors for searching what are the diseases and everything like that. Another important application with ultrafast lasers, and is also related with diagnostics, is that for this position emission tomography, you need to have some isotopes that need to be put it on the body to be able to do contrast, to be able to get images, because they have such a short lifetimes. Is very difficult for some isotopes to be used for certain hospitals. An isotope to be used in these PET systems can have a lifetime of 30 minutes. And this is quite complicated to deal with on the day-to-day, because it means that someone from the hospital needs to go to the facility, which is similar to a synchrotron, and they produce the isotopes, and they have to come back again to the hospital, and they have to do that in less than half an hour. So the isotopes are still radioactive, and they can do the imaging inside the patient. And the idea here is that using ultrafast lasers that you can place in a room in the hospital, you could be able to generate isotopes with different characteristics. So we can also trace other type of tissues and other type of, let's say, liquids and another type of diagnostics. So this could allow a hospital to increase the amount of diagnostics and capabilities to be able to understand or prevent people to have other important diseases. Okay, and this is the application I'm going to talk more about, because it's an application that we explore quite intensively for the past 2 years at the university, also with the company, with the Sphere. And this application is called two-photon microscopy. And basically, you also have an ultrafast laser, and you need also measurement and control. And for this, we would be able to image what is on the brain. At the moment, this has been done with mouses and other type of animals. Or you can use this also to image other type of samples, like, for example, real-time imaging of how a cell is processing a drug that is being inserted on this sample, and see all the dynamics of all the behaviors of the cell and the drug that is occurring on this lifetime imaging. So these studies are really very, very important because of the short pulse duration. We would also be able to study very fast interactions, like, for example, the neurons on the brain. So you would be able to understand how Parkinson or epilepsy or other such important diseases are happen to behave in the first place. So for doing two-photon microscopy, well, whenever we have a laser system, we need also to compress this laser system, and then we need a microscopy objective. Then this microscopy objective is focusing the beam in the focal plane, and then we are collecting the fluorescence of this sample. And to understand that in this focal plane, the laser has its best characteristics, we need to also measure here in plane how this laser system is behaving all along the path. And this is an example of a measuring head in the focal plane of a microscopy objective to be able to measure a pulse as short as 7 femtoseconds. And this is quite a unique result, and is very, very interesting because in the previous years it was very difficult to obtain 7 femtoseconds on the focal plane of a microscopy objective, because for microscopy, normally there are used longer pulses, like 140 femtoseconds or 200 femtoseconds, and they can be a little bit relaxed on the dispersion that they need to be managed to have the nice characteristics. However, we were able to have a system that we have 7 femtoseconds on focus, and this is very important because we are going to see important things and important advantage when you go to really very, very, very short pulses. So a system that can control a laser system is, as Dr. Elder showed previously on the previous talk, we can do it with a pair of watchers and sharp mirrors. And then we have the microscopy system, and we can put there a measuring head. So this we can put it into boxes. So we have a really very short 7 femtosecond laser system with a macro compressor, and then we can have this microscopy system with the measuring head on top, and we can do images with all these full equipment, like the laser, the compressor, which comprises the compressor and the measuring head, which we will call it the D micro, and we use the discount technology to be able to do that. And then we have a microscopy system to be able to do the images. So we have been working quite intensively in the two different wavelength ranges, one at 800 nanometers and another one at 1 micron. And this is a very special laser too, because it's a 20 femtosecond fiber laser system. And these two results here are measurements on the focus of the microscopy system, which is very, very, very important, that we keep the peak powers and we keep the short pulse durations on focus. And regarding this topic, I'm going to talk about the advantages of comparing two different laser systems. They both are femtosecond laser systems, but one is 7 femtosecond laser and the other one is 70 femtosecond laser system. And some of the examples I'm going to show here have been obtained in collaboration with INL. So this is the Institute of Nanotechnology here very close to Porto in Braga. And as you can see here, on the blue curve, we have the spectrum of a 7 femtosecond laser. As you can see here, this is a huge bandwidth. So this means that my pulse is going to be really, really, really short. It ranges from 650 to almost 1050. Also, we can show here in red, we have here a 70 femtosecond laser system. As you can see, the spectral content is quite short in comparison with the 7 femtosecond laser system. Also in this chart, I want to show you the absorption bands of different fluorophores. So we have the DAPI here, we have the Alexa, which is overlapping with the DAPI. We also have the ROS here. And as you can see, the 70 femtosecond laser system could be able to excite, because they are overlapping, the Alexa and the DAPI at the same time. But the 7 femtosecond laser system can also excite this fluorophore here. And this is very, very important, and I will show you later on what is the importance of this. So what I'm going to show you now is some examples of multiphoton images of a swing carotid. So what happened when you illuminate these samples, these swing carotid samples with a 7 femtosecond laser system, you cannot really resolve the core of the cell. However, if you use the 7 femtosecond, you are able to resolve much better. And the same with this image here, just for a narrow bandwidth. Also, if we compare these two temporal durations, and this is what is very, very important, and is that we have been testing that going to very short pulse durations, as short as sub-10 femtoseconds, we're also able to deeper imaging on the samples. So, and this is really, really, really very important, because with the 7 femtoseconds, we are here in 200, 250, but with the 7 femtoseconds, we are even deeper on the substrate. We have been going down to 650, and what was limiting us was also the working distance of the microscopy objective, because it could not focus farther away. And this is a very interesting result, that with shorter pulses, you can do deeper imaging on tissues. Also, with this technology, you can stitch pieces of images, and we can make a large image, which is very interesting to have a wider, with high resolution image, which is very, very, very interesting. So here, this is another example, another collaboration with, in this case, with the Francis Crick Institute and Thorlabs. This is a 10 femtosecond laser system provided by Thorlabs. And this was a 140 femtosecond laser system that the Crick Institute had his current laboratory. And what we realize is that the intensity of the pulses, where they are shorter, is much higher, and you can see more details on the image than when you use a 140 femtosecond laser system. And this was done in a mouse gut. And we can also see that the penetration in this case was quite different. And I'm going to show you in the next slide. So on the left side, you have a 140 femtosecond laser imaging, and on the right you have a 10 femtosecond laser imaging. And these are two videos, and this is starting, and now we are starting to see, and then we are starting to lose the image. So we have been, as long as we are playing the video, we are scanning deeper into the tissue. So I'm going to show you again, because this was very fast. So we have here image, and now we are starting to lose it. However, if we use a 10 femtosecond laser system, we are starting to see image, and we are going down and down and down and down in tissue. We still have information. We are able to have information for a longer time. And this is very important, because whenever you have a piece or a sample that you want to image, you don't want to cut it. You want to keep it as wide as you can, and you want to see inside as deeper as you are able to do it. Another example here is also showing an image of Alexa 488, and this image was taken using a narrow line laser system, which is a 48 nanometers argon system. This one was taken with a 140 femtosecond laser system. As you can see, the image is quite blurred. You cannot see a lot what is happening, what is going on in here. And lastly, the same image taken with a 10 femtosecond, we can see that the details are more defined, and you can see better the structure of all the parts in here. And this also confirms that really going to very short pulse duration with the right control of the laser system allow us to have more knitted images, more details shown on the image, which allow us to being able to detect better if there is any problem, or if there is something wrong with this sample or specimen that we are testing with the microscope system. Another example here is something very, very, very important, which is the photo bleaching. So scientists spend a long time preparing samples and put it on the microscope slabs and fixing and preparing everything. And the problem is because laser systems have so much average power that they damage these samples very easily. And the example here is I'm sorry, but it's a live larva, and we are going to show what happened with this live larva that is being inspected using a 140 femtosecond laser and a 10 femtosecond laser. I'm gonna put this first. So as you can see, we are seeing that the laser is actually burning the larva here, because it's too much energy to be able to get the images, because as we showed before, a long pulse has a lower peak power, so we need to increase the energy so this peak power can increase. However, if we use a very short laser system, you don't need to increase the average power, so you don't burn around, you don't damage your sample so easily. And this is the example with the 10 femtosecond. As you can see, there is some photo bleaching, but it's not as severe as you can really damage the full structure. There is still some parts of the sample that can be seen. in comparison with the other specimen that really was completely destroyed and damaged. So in resume, I think I was too quick. In resume, I showed you a summary of how ultra broadband femtosecond laser systems can be really interested for medical applications and therapy and diagnostics. I haven't included here, for example, things like the LASIK technology that is very well known and is very widely used in every hospital, that they are able to cut our eye, the surface of the eye, take it out the lens, and put another one, put back the surface of the eye, and cutter it, and doing it without really damaging so much the eye. And the full idea here with ultra fast lasers and short lasers is that the shorter the pulse, the higher the intensity, you are able to access nonlinear effects without burning or without destroying severely all the surface around. And this is super important whenever you want to do a surgery in a hospital, sorry, and you want to recover fast. So if you don't damage the tissues around your damaged area, your recovery is going to be faster, because you only have a small portion that needs to heal. So this is very important for medical applications. And the other thing about ultra fast, ultra intense femtosecond laser systems is that they are in a level of compactness that they can be installed in hospitals. And this is very important, because we can bring this technology to different places that in some years ago was impossible, because a synchrotron is a huge building with very expensive, and there is a few of them in the world. Also, regarding these femtosecond lasers, really focus on nonlinear microscopy, allow us for longer measurement times because they have lower thermal effects. Something super important, allow us to go deeper in the tissue, which is very important to understand what is happening with the sample. And also we can explore for multi-fluorophore excitation and with a single laser source, instead of using different lasers to be able to excite different fluorophores at the same time. I didn't went very deep into this, but this is also very interesting approach. And I also wanted to thank everybody on these collaborations, because this is a course, of course, and you are learning how to use femtosecond lasers. But it's important that for us that we provide these courses to thank all the people that allow us to bring technology to a different level of expertise. Okay, and I think I will finish my presentation, and I will thank you, the organization, and all of you for being here today. Thank you very much.
Sorry, Professor, you've got some questions. You can read it in the chat.
Yes, sorry, I could not read while I was presenting. So can you please expand on the sentences for the application of the both of the microscopy? So what do you want to expand? The use of the lasers, the use of the applications, what kind of microscopy we can do?
Maybe you can jump to the second question while the students are
Yeah, so just for finishing the first one, so the design, the systems for ultrashort pulses in microscopy, basically for a microscope to use with ultrashort laser pulses has to have a different management on dispersion. So we really need to be very careful on what kind of optics are we using there, and try to reduce the dispersion on these optics. For example, if you need a beam expander because the beam of the ultrafast laser is very short, the beam of the ultrafast laser is very short, and you want to use lenses to do a telescope, instead of using lenses, it's good that you use reflective optics, for example, and there we can reduce the dispersion on the system. How exactly the pulses improve on the resolution? This is what I show here. So here, for example, you have in the physical phenomena. I don't know if you can see my screen yet. Yes, I hope so. I'm gonna make it bigger so I can see the questions. So for example, here, these two images, because this laser has a lower peak power than this laser here, because it has a really huge peak power, you need a huge average power to be able to get the nonlinear excitation the same level as this laser here. And this is mainly the huge difference between one and the other. And this is how you can improve, let's say, the resolution, because you are imaging with a high peak power without damaging what is around the laser system. Okay, now I'm going to question 2. How do you prevent the sun not using a high peak power ultrafast? Plasma, there is the confusion. Okay, the plasma. So I confused with the plasma in the paper. I wanted to be more illustrative for the cutting applications and not for diagnostic applications. So normally for cutting applications, you need a much higher peak power, so you are able to ablate and to remove material. For diagnostics, of course, the peak power is high enough to be able to excite the nonlinear effect that allows you to perform the imaging. If it is a second harmonic generation, if it is a lifetime measurement, it really depends on the way you are taking the image from the sample. So sorry about the plasma. It was just to show that you can cut paper without burning it. So this was like an example for explanation. It's not supposed to cut the samples when you are trying to image them. But actually, this is what it happens when you have the larvas here. With the larvas, this is what is happening. So it's so much average power that you're actually burning them because of that. But this doesn't happen when you have a really, really short pulse duration. Well, I hope I could answer the questions. Okay, thank you very much to all of you, and I wish you a nice day. Bye-bye.